When evaluating quadratic expressions, the order of operations can help us interpret these expressions in useful ways. For example, for a quadratic in standard form, we know that there are generally three terms separated by addition and subtraction. And since addition and subtraction are the final step in the order of operations, we can interpret the standard form as three separate expressions that we can evaluate independently. Then, once we have a value for all three expressions, we can finish the problem off by adding and subtracting as necessary. In the factored form, the grouping symbols indicate that we have two independent expressions that we can once again evaluate individually. Then, once we have a value for each expression, we multiply the results to get our final value. No matter what form of a quadratic we're looking at, we'll pay close attention to the order of operations and how those rules can help us evaluate the expression in question. To kick things off, let's look at three different quadratic functions and evaluate each of those functions at a couple values. As we write these functions, notice that f is in standard form, g is in factored form, and h is in vertex form. Then, we'll start by evaluating f of 4. When we do this, we're going to replace both x's with the number 4, and we're going to put those 4's in parentheses. At this point, we can think of our three terms as three separate expressions, where the first two expressions need to be further evaluated. For the first term, notice that when we put our input value in parentheses, we don't actually have anything to calculate inside the parentheses. So we can move on to our operations outside the parentheses, which are multiplication by -2 and squaring. Anytime we have an exponent, we should ask ourselves, what is the exponent attached to? In this case, the exponent is attached to the parentheses, so we should square everything inside the parentheses. This means that we do 4 times 4, which is 16. Then, we multiply the 16 by -2 to get -32. Now, we're ready to look at our next term, and the only thing to do there is to multiply the 5 and the 4, which gets us 20. We can then see that we have a value for each of our three terms, so we can finish things off by doing the appropriate addition and subtraction to get our answer of -13. Let's do one more evaluation with this function, and as we do so, you'll eventually see that the first term still has a negative value, like it did in the first evaluation. This is because we're squaring the -3, which means that we take -3 times -3, which is +9. Then we multiply that by -2, which gets us -18. Basically, when we multiply by several negative numbers in a row, our results alternate between being positive and negative. So we need to be mindful of keeping close track of the sign of the resulting expression. For our next function, let's start things off there with g of 10. As we indicated in the introduction to this video, we can think of this expression as being composed of two sub-expressions. So we'll start by just thinking about the evaluation of 3 times 10 plus 7, which works out to be 37. Then, we'll forget about the 37 for a moment and just worry about evaluating 10 minus 8, which is 2. Once we have those two answers, we can multiply them to get our final value of 74. The same principles apply if we're evaluating a negative number. Sure, it'll take a bit more work to make sure we're managing our negative signs correctly, but overall, we still just have two linear expressions to evaluate and then multiply. For our final function on this screen, let's start with h of -8. Notice here that the exponent is once again attached to a set of parentheses, but this time we actually have an expression inside the parentheses to evaluate. So let's start by evaluating the inside of the parentheses and follow that up by squaring. Then we can multiply by 5 and add 6 to get our final value of 86. And for one more example of that process, here's the calculation for h of 6. Now that we've done some basic evaluations, let's do a few more examples that contain some calculations with fractions and decimals. Notice in our first function that we can think of the function rule as being in standard or vertex form. Whichever way we think of it though, it won't really change how we calculate our answer. So let's start with f of 2/3, which involves taking 2/3 times 2/3, which is 4/9. Then we need to subtract 9, which can be rewritten as 81 over 9. This gets us a final answer of negative 77 over 9. Next, let's do f of 3.2. This would be a good time to use a calculator if you're working things out on your own, and eventually you should get an answer of 1.24. Then, let's go to g and start with g of 8. Notice that g is once again in the factored form, but this time there's an additional constant factor at the beginning of the function rule. This shouldn't affect our calculations much though, since we can initially just ignore the 2 and focus on determining the value of the other 2 factors. Then, when we have a value for each factor, we just need to multiply 3 numbers instead of 2, which in this case gets us 168. And if we wanted to plug a fraction into g, here's what that would look like. And finally, we have our h function, which is quadratic, but is not in any particular form. It does look kind of like the factored form, so we can initially think of it that way, but we'll just have to add one little constant at the end of the process. Whatever way we want to think about it, we'll probably need to use a calculator at certain points when evaluating h of 6. However, h of 9/4 turns out to have surprisingly nice numbers when we evaluate it, and we end up getting a value of 67 over 8. Now that we've evaluated several quadratic functions, it's time to take a look at how quadratics fit in with the idea of a function machine. So as we've done before, let's check out some function notation and try to convert it into a function machine, starting with a function that's in the standard form. To do this, we need to ask ourselves, what sequence of steps is happening to the input of the function? But there's a problem with this question because the input of the function, which is x, shows up twice in the function rule. And because of that, it turns out that the concept of a function machine as a sequence of steps breaks down, meaning that we can't represent this function with a machine. Is there a way that we could restructure how we build a function machine to fit this situation? Sure, it's probably possible, but it would likely be more work than it's worth, so we won't be doing that here. Instead, we'll recognize the limitations of function machines and stick with function notation when it comes to the standard form. The same goes for the factored form. Since the input of the function shows up twice in the function rule, there isn't a way to represent this function as a sequence of steps in its current form. And so we'll also avoid function machines as a way to represent the factored form and stick with function notation for that form as well. You've probably noticed, though, that we haven't talked about the vertex form yet. In fact, if we think back to our work with the vertex form in our previous video, an important characteristic of that form was that the variable only appeared once. This turns out to be an extremely useful characteristic, and one way this usefulness shows through is when working with function machines. Take this function, for example. If we want to convert this into a machine, we simply look at our input in the function rule and see what steps happen to it. The first step is that we're subtracting 3 from the input, and then our next step is to square that result. After that, we multiply by 5, and then we finish off by adding 12. One thing to note here is the symbol that we used to indicate the exponent of 2. That symbol is called a caret, and since it looks like an arrow pointing upwards, it's a common way to indicate exponents, which are typically raised up to the superscript position. Now, let's do this process in reverse. If we're given this function machine, we can write out the function notation by plugging a variable into the function. And to mix things up a bit, let's use t as our input, since that's another commonly used input variable. Then, as we move through each step of our function machine, we get a new expression that represents the steps of the function up to that point. And once we get our output, we can say that y of t is equal to the output, which is -2 times t plus 8 squared minus 1. To conclude this video, let's make some extended tables of values to get a bit more practice with evaluating quadratic expressions. We'll start things off with one of the vertex form functions from our previous screen. And as we create our extended table, we'll fill in the column headers by following the sequence of steps that we identified when making our machine for this function. Once we have our table made and our columns labeled, we just need to choose some inputs and evaluate. For the sake of observing some patterns related to quadratics, let's choose our inputs to be the integers from 0 to 6. Then, when we subtract 3 from each input to find the value that belongs in the second column, we can see that we get the integers from -3 to 3. At this point, we need to square each of these values, but let's start from 0 and work our way up before looking at the negative numbers. 0 squared is just 0 times 0, which is 0. Similarly, we do 1 times 1, 2 times 2, and 3 times 3 to get 1, 4, and 9 respectively. Then, when we go to the negatives, we get -1 times -1, -2 times -2, and -3 times -3, which are also 1, 4, and 9. Notice that similar to the absolute value, none of our values after squaring are negative, since a negative number times a negative number results in a positive number. Additionally, the result of squaring any number is the same as the result of squaring the negation of that number. These properties can be summarized this way, but note that we're specifically talking about real numbers here, so these properties aren't necessarily true for other types of numbers. From here, we need to multiply each value from the third column by 5. And since certain values in the third column are repeated, we'll also have several repeated values in the fourth column. And finally, we can add 12 to achieve our final outputs, which completes our extended table for the vertex form. Now, let's go back to the standard form function that we were unable to make a machine for since the function couldn't be represented as a sequence of steps. You might think that this would also make it a challenge to make an extended table of values, because the columns in our extended table usually mirror our sequence of steps. Thankfully, though, this isn't a requirement for tables. Even though that is how we've constructed our tables up to this point, each column doesn't have to directly follow from the previous column. This allows us to make a table that looks something like this. Notice that the second, third, and fourth columns each represent a term from the standard form. In fact, before we even choose our inputs, we're able to fill in this fourth column with -5s, since that term doesn't depend on the input at all. Then, we'll choose our inputs to be the integers from -3 to 3, which will make our calculations for the second column very familiar. Next, we need to fill in the third column, but notice that this column is just 2 times the original input. So instead of looking at the previous column like we typically do, we're going to look back to our first column of inputs and double each of those values. Once we do that, we're ready to calculate our final output which is the sum of these three columns. So we'll add up those three values for each row and write down the final output values. With that, let's make one final table for a function that's in the factored form. As always, our first column will contain our inputs, but for our second column, let's have that represent the first linear factor of our function. Then, since the second linear factor contains a couple calculations, let's break that down and make our next column represent the input times 2. Then, the following column can represent that value plus 1. At this point, we need to multiply the values from our second column and our fourth column, which will give us our final outputs. Now, depending on how comfortable you are with these calculations, you might be able to skip this column. Or you might even be able to skip the intermediate columns altogether. The purpose of these extended tables is primarily to break our calculations into smaller steps. So if you're able to skip over some or all of those steps, feel free to do so. But if you find these extra columns helpful, then utilize them as necessary. That concludes this video on evaluating quadratic expressions. Hope you learned something new, and thanks for watching.